So let's now consider one last problem with a rod of charge Q and length L. This time, though, the density of the rod will be varying, and we're given the function for that, lambda equals alpha x, where, of course, I should specify where x equals 0 is located. And suppose again that we revisit our first problem where we wanted to find the field a distance a away from the rod. So the first question I can ask, which hasn't really been asked before, is one, what is alpha in terms of Q and L? And this is where we encounter a new concept, namely that of charge normalization. So let's recall that lambda is equal to dq by dl, or in this case, because we're aligned along the x-axis, it is also equal to dq by dx. Therefore, if I have a total charge of q, remember that capital Q is simply integral dq. And therefore, I can say capital Q must equal integral. Remember that our particular value for lambda in this problem was given as alpha x, and therefore capital Q must equal alpha x dx, integrating along our rod from 0 to L. Going ahead and integrating that, we get alpha over 2 L squared must equal Q. And therefore we can say alpha is equal to 2Q over L squared. Good. So we call this process, for your reference, charge normalization. And so moving on to our next question, or our main question, let us find the electric field at point A. And I'm going to go through this one fairly quickly because you can revisit our first problem and follow along with most of the steps there. We begin with our representative dq. We indicate the distance to our point of interest. Our coordinate system will be a bit different than the first time we did this problem, so we'll pay particular attention to that. But we start from saying dE is equal to integral k dq over r squared. We ended up going all the way to saying we can rewrite this as integral k lambda dx over r squared. Now, in the past, we rewrote lambda as q over L. In this case, lambda is not constant, so it must be rewritten as alpha x dx over r squared. Moreover, we know the value of alpha, 2q over L squared, so we can also pull that out. So we have 2kq over L squared times integral x dx over r squared. So one last step, we need to think about how r varies with respect to x, and for that we'll rely on our diagram. I've indicated r. We have our arbitrary x coordinate over here. And what we'll notice is that x plus r, which denotes our entire distance from x equals 0 to the point at which we want our electric field, is equal to L plus a. And therefore, we can rewrite r as, well, actually, let's bring along our 2kq over L squared, integral x dx over L plus a minus x squared. Finally, our bounds of integration in this case will be from 0 up to L.